this video we are going to study the propagation of light, electromagnetic waves, or massless particles in general in the framework of the parametrized post-Newtonian formalism. I should say that we are going to study the propagation of light only in the field, in a static spherically symmetric field. The one produced by a point particle, the one that we determined before. Okay, so the propagation of light is determined by the geodesic equation plus what we usually call the mass shell condition, u mu x dot nu equal to 0, that tells us that the tangent vectors to the world line are null vectors. When we deal with the post-Newtonian approximation, we are interested in using time, the coordinate time, as the evolution parameter. So x dot mu here is dx mu dt. The fact that this vector is null does not depend on the parameterization. If you reparameterize x mu, you only get a factor here squared from the change of variable, and this is still 0. So the condition is still the same, even if this is time. However, clearly the coordinate time in general is not the affine parameter of the null geodesic, and we will have to take into account that fact when we deal with the geodesic equation, because we know that if we don't use the affine parameter, there is a right-hand side, okay, which we cannot ignore. So, okay, let us expand this expression in this post-Newtonian approximation, and we know that this will be x dot 0, g0, 0, x dot 0 squared. Then there is a g0i, but for the static spherically symmetric field at the lowest order, this is 0, the off diagonal term, and then we only need to consider this one. Okay, the derivative of x0 with respect to t is just c, so this is c squared g00 plus gij x dot I x dot j. That, well, we can write as vi and vj. Okay, now this is c squared, and g00 is 1 minus 2u divided by c squared plus 2 beta u squared divided by c4 plus terms of higher order minus delta ij 1 plus 2 gamma u divided by c squared vi vj, okay, plus terms of order 1 over c4. And here I have already used this static spherically symmetric field. We know that it is like that, otherwise there would be more parameters and other gravitational potentials. Okay, so since this is going to be 0 up to terms of order 1 over c4, then if we divide this whole expression by c squared, we get 1 minus 2u divided by c squared plus 2 beta u squared divided by c4 minus 1 plus 2 gamma u divided by c squared. Here we can add terms of, just to take them into account that they are there, v divided by c squared is equal to 0. Okay, so this is the expression. Okay, now we can invert this, and you find that v divided by c, okay, is equal to 1 minus 2u divided by c squared plus 2 beta u squared divided by c4. and this multiplied by 1 minus 2 gamma u divided by c squared plus terms of order 1 over c4. Okay, so this square. And then you can see that it is not consistent to keep this term here, so we just ignore it. And okay, you get 1 minus, and you get here this 2 and this 2 gamma, so 2 gamma plus 1 u divided by c squared plus terms of order 1 over c4. Okay. So now that we have found the absolute value of the velocity, okay, we can do the following. We can express the velocity, if you want, as vi. Well, let me put it this way: it's vi divided by v, obviously. Okay, using this formula here, v is c times 1 minus 2 gamma plus 1 u divided by c squared, and vi over v, is to the power 1/2. Okay, so we can approximate it to this order like this. It's just minus, and we call vi divided by v ni. These plus terms of order 1 over c cube. Okay, so this is the next expression that we want. This ni is such that ni is 1. That's the idea. It's just pointing to it's a vector that points into the direction of motion, but it has absolute value 1. Okay, so this is what we are going to use in the geodesic equations. Let me write the geodesic equations, but now splitting them into time and space components, and taking into account the fact that this time coordinate is not the affine parameter. Okay, so the geodesic equations, well, I'm using something else, some other variable, so mu alpha x dot mu x dot nu. Now this is not 0, it's some function, okay, times x dot alpha. This is the autoparallel equation of this, or the geodesic equation in an arbitrary non-affine parametrization, which is the case because now x dot is the derivative with respect to the coordinate time. So now we split this equation into 2, okay, for alpha equal to 0, and for alpha equal to I. Okay, so we start with this one. X dot 0 was c, so x double dot is 0. And then we have, okay, gamma 0, 0, 0. We will have x dot squared, but remember that gamma 0, 0, 0 for this kind of metric was just 0, plus 2 times gamma 0 I 0. X dot 0 is c, and then x dot I is vi, and finally we have gamma ij 0, which was again this could come multiplied by vi and vj, but the gamma I 0 was 0 for this metric. Okay, and x dot 0f is just cf. Since we have the expansion of these Christoffel symbols, we use it. Okay, this gamma 0I is minus 1 over c squared partial I u, plus 2 times 1 over C4 beta minus 1 U di U C VI, and this is equal to CF. Since we are going to stay at lower order than before, this term we ignore. Okay, this is minus 2 over C VI diu, and this is the value of CF, but we have an expression for VI, which is this one, so this is minus 2, 1 minus gamma plus 1 divided by C squared U, and this is Ni diu, and this is the expression for CF, okay, which is something that we can evidently use here. Okay, this equation becomes an equation for VI, the derivative of VI, and then, well, we expand this as usual. We have x dot 0 squared, which is C squared, plus 2 times 0 ji x dot I, which this is C, but okay, who cares, because we know that this component of the connection is 0, and then we have jki vj vk, and this is equal to f vi. Okay, now we just have to substitute the expressions that we obtained for these components of the connection, and this I am not going to do. It's just trivial, okay, but more or less long calculation, and the only thing that you have to do all the time is to replace VI by this expression, which is this factor times Ni, and in the end replace F by this expression here. The result is an equation, and also you have to substitute VI by this expression involving Ni here, and with that you just get an equation for the derivative of Ni, which is the equation that dictates the propagation of light in this parameterized post-Newtonian formalism at the lowest order. Okay, so this 1 over C squared, and this is the main equation we will have to deal with. Okay, if we had done this for general relativity, we would have obtained a factor of 2 instead of gamma plus 1. Now, all the experiments that can be done with light in which this equation is relevant will constrain the value of the parameter gamma experimentally. This is basically what the Cassini experiment that we will explain later has done for this parameter gamma with the highest precision so far. Now, a consistency condition of this equation is that if you multiply both sides of the equation by Ni, you get 0. You see that this is the projector on the directions orthogonal to Ni. You multiply by Ni, and since this is 1, it gives you 0. And Ni, the Ni is just a half of dn squared, which is 1, which is constant. So this is 0 as well. So both sides are 0. And this provides a consistency condition of this equation. Now we are going to solve this equation iteratively, order by ordering 1 over C. At lowest order, the equation becomes just dni over dt equal to 0, and the solution is just ni equal to some constant vector ki. Okay, this ki will be equal to 1 the absolute value. And once you have the solution for Ni, you go to the expression for Vi. Remember that Vi is just V times Ni, but V is this expression here, C times 1 over, and the next term is of higher ordering 1 over C squared, so this is just C. Okay, so this is Cni, and in the end this is Cky to this order. Okay, now you integrate this and you find that xi, okay, remember that this is dxi over dt. Xi is nothing but a constant, the origin of this radiation of the light ray, so xi emission plus Cki t minus t emission, okay, plus terms of higher order, which here are of order 1 over c. This is the idea here. The approximation is plus terms of order 1 over c squared. There is this rule of thumb that tells us that these orders are even or odd, okay? So in fact here this should be, I think, cube. Okay, so this is the lowest order solution. Let me call this particular solution just x tilde, okay, because then we are going to use it in the next iteration. So in the next iteration, you consider that Ni will be the lowest order solution, Ki, plus a term of order 1 over c squared, which I write explicitly, and that I call alpha I, okay, then plus terms of order 1 over c4. If you look into Poisson and Will's book, instead of 1 over c squared alpha I, you just see alpha I, but I think it is convenient to keep the 1 over c squared and to remember what is the order at which this term appears explicitly. Now you plug this Ni into the equation here, and since Ki is constant, you get that the 1 over c squared d alpha I dt. Okay, you have plugged this solution as an ansatz here everywhere. Okay, you have 1 gamma plus 1 divided by c delta ij minus, and then you substitute here the solution for Ni. This is Ki Kj minus 2 over c squared Ki alpha j symmetrized minus terms of higher order that we will discard. Okay, partial j u, where this u is evaluated at the lowest order solution. Okay, plus terms of order 1 over c squared, c cube, sorry. This means that this order we should discard not just these terms here, but also these terms, and we have just for alpha I this equation. Alpha I is determined by the solution to this equation. Delta ij minus Ki Kj partial j u evaluated at the lowest order solution that we denote by x tilde. Now that we have this equation, okay, and we have Ni, so implicitly we have alpha I, we know how to solve this equation, which is what we will do in a little while. We can reconstruct Vi. So Vi is V times Ni, and V is given by C times 1 minus gamma plus 1 u divided by c squared, C times 1 minus gamma plus 1 u divided by c squared, and Ni is ki plus 1 over c squared alpha I plus terms of higher order. Now if you expand this expression, you find first of all this factor 1 minus gamma plus 1 u divided by c squared multiplying c ki, but then in the next term, the next order, this times this is of an order too high, and this will be 1 over c alpha I, then plus terms of order 1 over c cubed that we are not going to consider. Okay, this the product of this term with u and alpha I would already be of this order 1 over c cubed. This term, okay, takes care of the longitudinal effects. Of gravity on the light ray. Longitudinal in this case means in the original direction of the light ray, which is ki, because we are going to impose that alpha I at time 0 or time at emission time, Te, is 0. Okay, so it starts with a certain ki, and then this alpha I grows and changes the direction of the light ray. But all the effects that are produced in the direction of the original light ray, which is ki, will be called longitudinal effects. And then this alpha I is transverse. Okay, takes care of the transverse effects. We will study these two terms more precisely later. Okay. But now I realize that I haven't explained why is this transverse. And the reason is that I didn't explain when I introduced this alpha I as an ansatz that n squared has to be 1. This implies that ki and alpha I have to be, this product has to be 0. Okay, because we know that to order 1 over c squared, ki is 1. Okay, so this means that alpha is transverse with respect to the original direction of the light ray, and this is what we call it transverse. A consistency check that indeed alpha I is transverse with respect to ki is that if you multiply this equation by ki, since this piece is a projector in the directions perpendicular to ki, automatically this is 0. So this has to be, this product ki alpha I has to be either constant, okay, that we don't expect it to be constant, or 0. So this provides this consistency check, and this is why we call this term transverse, and it will describe all the transverse effects produced by gravity on the light ray. Now the next step, okay, will be, this is what we want, and we will apply it to study longitudinal effects, transverse effects, and so on, is to study the solutions of this equation, how to solve it. For this, we need the partial derivatives of the Newtonian potential, which we remember, okay, was given by this integral, just because it is the solution to the Poisson equation. Okay, so if I now take derivatives, of course, with respect to the x's, then the only thing that is affected here is this term 1 over x minus y, and okay, the derivative of this is well known. You get a minus sign, you get xi minus yi, and this cube. Okay, so This is di of u, and now you plug this into the equation, and you get that the alpha I dt is gamma plus 1 c, the minus and the g, the integral d3y rho star dy, and then the projector delta ij minus kj, which is acting on xj minus yj, and all this divided by x minus y absolute value cube. Okay, and remember that here we are supposed to replace x by x tilde everywhere. Okay, so if you want, we can write this explicitly, because this was the approximation that we were making at this order. Okay, this means that since x tilde, we have it here, okay, it's just xie plus a term proportional to ki, and this is the projector in the directions orthogonal to ki. Only the term xje survives. Okay, so we can replace this by this term alone, and we are going to call this projection, okay, this is the distance from the point of integration y to the point of emission projected in the directions perpendicular to ki. We are going to call this bi, which is of course related to the impact parameter, and this is why we are using this notation b. Another notation that we are going to use, just because this term appears many times, is SEI, and for some reason it disappears. Okay. The fact that this BI is the impact parameter, well, if here this is the emission point, okay, this is some point y where we are integrating, okay, and then this is the vector SE. If the direction of emission, the original one, is this k, observe that we are projecting in the direction perpendicular. This vector SE is projecting in directions perpendicular to k. Okay, this is the perpendicular. So this is okay. Let me see how this is connected. This is the perpendicular. Maybe I should move all this to another place. Okay, so this is the direction of the light ray, and okay, the perpendicular that comes through this, and you see that okay, this would be the projection. All this piece would be the projection up to here, the projection of SE along the propagation direction, the initial propagation direction, and the this is PE. This is the projection in the perpendicular direction, and clearly this is the impact parameter. Okay, here this is expressed as a vector. The absolute value will be the impact parameter. Okay, sorry for my drawings. You can also interpret the impact parameter as the distance from a given point. Here is y, so this p is a function, is not a constant. Is the smallest distance to the light ray. The distance when you are have the closest approach to the light ray. Okay, this would be B. So B is the impact parameter. Okay, so with all these definitions, the equation now takes this form. Rho star Ty. This is x minus y cube, and this is just Bi. Then we introduce a bit more notation in order to simplify further the expression. We call this S, this vector S in general. Okay, so this would be the vector inside. So S is x minus y, so SE is a particular case when x takes is the position of the emission. So with this definition, this would be S cube. Okay, then in order to integrate this in general, well, you don't want, it's not that you want to integrate it, you want to rewrite the right hand side as a total derivative with respect to time, so you can integrate the differential equation in the most trivial way. For this, you need to use a trick, and the trick is that this derivative of Si Ki divided by S is given by B squared divided by S cubed plus terms of order 1 over C squared. Okay, this is what you have to use. And here we have this S cube, so I can replace this S cube here using this property by okay, 1 over C, so this C goes away, Bi stays, okay, but I have to divide by B squared, and then I have the derivative with respect to time of Sj Kj divided by S. Okay, then the next thing is to realize that this whole thing now is this total derivative can come out of the integral. Okay, so first of all, I can put this inside of the differential, and also this, because at the order at which we are working, derivatives with respect to time of the density of the Earth's mass density, because I am assuming this is, we are in this slow motion approximation, this has to be, these derivatives of rho star have to be of a higher order in 1 over C, and you also expect the same of the derivatives of the impact parameter. So at the order at which we are working, we can write that d alpha I dt is the derivative of everything that you have in the integral. Okay, so alpha I is just minus gamma plus 1 g, the integral of rho star Ty Bi over B squared Sj Kj divided by S, and now minus whatever, plus, if you want, but plus an integration constant, but you can choose this so that alpha I at emission time is 0, and when you do this, you find an expression. If you impose this, you find an expression which is identical to this, but evaluated at emission time. So you can write all this, as Sj divided by S minus Sej divided by Se and multiplied by Kj. And this satisfies this initial condition. Okay, so we have found the expression for alpha I that we were after. The next step would be to obtain Vi from this, and you can also obtain Xi by integrating now alpha I and so on. However, okay, we will do this later when we need it. But the first thing that we are going to study now, which is just the deflection of light by the gravitational field in this post-Newtonian approximation, can be computed without having to integrate alpha I again. Okay, so this is what we are going to do next. In this case, in the case of the light deflection by a spherical body, which is the one that we are implicitly studying from the beginning because of the form that we have assumed for the post-Newtonian expansion of the metric, the rest mass density is just the mass of the body times a delta function at the origin. Again, this is an approximation. Okay, and in this case, we can immediately integrate, perform this integral here for alpha I. So alpha I could be minus gamma plus 1 g, and we evaluate, we replace essentially y by x, sorry, by 0 everywhere. Okay, so we get Bi, there is an m from here, from rho delta, and then there is Bi over B squared. And Si, remember that Si was x minus y. So we just eliminate this y because okay, what we are doing is to replace this by this delta. So wherever there is a y, we just write 0. Well, if I write vectors, this is what I have to write. Okay, and then this is nothing but xj. S becomes just the absolute value of x minus xj emission divided by x emission, and everything multiplied by kj. And okay, maybe I should have been more precise. Everything in the right hand side here was assumed to be evaluated at x tilde, so perhaps I should have written explicitly tildes everywhere. Okay, so here this is x tilde. X tilde, I remind you that it's just xi e at emission plus c times ki t minus t emission plus terms of order 1 over c. Okay, so this is the expression for alpha I, and Bi. Okay, remember that it was the projection in the direction orthogonal to Ki, so this is the projector, and what you have here in the past that was Si e, okay, and now what remains is just x ke. Okay, so this is the complete solution for alpha. And this is all we need to compute the angle of deflection of a light ray that passes near the sun or any other spherical object that gravitates. First, we need to make a drawing to explain what is the general setup and to appreciate the geometrical definitions better. So let me show you the drawing. Here I have represented the sun, and which is at the center of coordinates. Okay, this is at the center of coordinates. This is something that we have chosen the moment we wrote this delta. The red line is the x-axis, Okay, so the emission point doesn't need to be over the x-axis. That would be a simplification, but we don't really need it. Light is emitted with this in this direction, k, okay, and x tilde is this trajectory that at some point has these dashed lines. Okay, the real trajectory is the black continuous line. Now the position vector of this original trajectory, okay, the unperturbed one, is x tilde. So at the emission time, the vector that tells you what the position of the light is, it is where the emission takes place, is x tilde e. If you want, this is x of t e. Then, well, it evolves, and an important thing is that when x tilde, when time goes to infinity, okay, the vector x tilde becomes essentially parallel to k, okay, when t is large enough. Another thing that another approximation that we are going to take is that b is much smaller, okay, in absolute value, than x tilde e. Okay, so the emission point is much further away than the impact parameter. This is, for instance, the situation when you study the deflection of the light coming from a star, and that just grazes the surface of the sun. Okay, so the impact parameter is essentially the radius of the sun, but the distance is much higher. It says light years with respect to millions of kilometers, of hundreds of thousands of kilometers. Okay, so this is the general situation, and now we are going to define an angle, the angle phi of t. This is an angle that changes with time, and that is the angle that x tilde and k have. Okay, so the cosine of phi of t is just the scalar product of xi ki divided by x. Remember that the absolute value of k is 1 to the order approximation in which we are working. If b is much smaller than xe, as we are assuming, then at the emission time, this is something that you can actually see. If this b becomes smaller, this line gets much closer to the sun, and the difference between the angle that xe forms with the x-axis and k forms with the x-axis goes to 0. So one thing that we see is that the cosine of phi at te is more or less minus 1, okay, because it essentially becomes pi if you want. So this is one approximation that we are going to take, and the other thing is if we come here, okay, here we can rewrite the expression for alpha I in terms of this would be the cosine of phi t, and this would be the cosine of phi at the emission time that we said it is 1. Okay, so let me copy this expression. Okay, so in this situation, alpha I is minus gamma plus 1 gm pi divided by b squared, and this is cosine phi t minus cosine phi te, but as we said, this is approximately minus 1, so I can replace this whole thing by 1 plus cosine phi. Okay. On the other hand, when t goes to infinity, cosine of phi, okay, let me see that this goes, when t goes to infinity, this goes to 1 because, as I said, x and k become parallel asymptotically. This means that, let me express it like this, alpha I, when t goes to infinity, goes to minus 1 plus 1, gamma plus 1 gm bi divided by b squared, and then a factor of 2. So it is minus 2. Okay, the last thing that we need to do is to, think what is the angle here, okay? The deflection angle, and this deflection angle is clearly this angle here that is typically called alpha. Is the angle between k and the final direction of the light ray. Okay, for this angle, since it will be very small, we are working in this post-Newtonian approximation, weak field, and so on. So it will be smaller. You can approximate it by the tangent, and the tangent of this angle you can take as the limit when t goes to infinity of the product of ni with in the direction of the impact parameter divided by the product, the scalar product of ni with the original direction of the light ray. Essentially, the triangle that we are studying is this one where, we are taking this side which is parallel to bi, okay, as a vector. Bi is like this, and then you project, in order to find this side, you have to project over bi divided by the absolute value, and in order to project on this side, you need to project with ki, which already has absolute value 1, and the quotient gives you the tangent of this angle alpha. But then we have an expression for ni. Okay, remember that ni, in black maybe, ni is ki plus alpha I divided by c squared. To this order of approximation, this is ki, and we just computed the value of alpha I, and this is given here. It is minus 2 gamma plus 1 gm bi divided by b squared, and then we have another factor of c squared, this factor here. Okay, so if you multiply this by bi, remember that bi was obtained by projecting something in the directions perpendicular to ki. So this term will not contribute because the product will be 0, and here you have bi divided by b squared. Okay, so bi is just minus 2 gamma plus 1 gm divided by c squared. Okay, on the other hand, if instead of this I multiply by ki, I know that bi is again projected in the directions perpendicular to ki, so this term does not contribute, and I get 1. So alpha, and I only interested in the absolute value, is given by 2 times gamma plus 1 gm divided by c squared to this order of approximation. So for general relativity, gamma is 1, and what you get is 4 gm divided by c squared, and this is the deflection angle. In the recommended reading in the program, you have several references to the experiments that measure this deflection angle with the sun. And you know that the first time this was measured was in this total eclipse of 1919, but it was also measured a few years ago because there was another total eclipse. The problem with this kind of experiment is that light has to graze the surface of the sun, and the surface of the sun is not really a clean surface. There is an atmosphere, there are lots of processes taking place there, and they act on light, okay? So it is not clear. There are some people who even say that the result of the 1919 experiment was not really that conclusive, that it's in the margins of error of the experiment are larger than the effect that you want to measure. So this is not the best, maybe not the best example of a test of general relativity. It is a test in the sense that, well, you really see an effect. Okay, light is deflected. You see a star that should be behind the sun. So light gravitates, and but this is, as we know, a general consequence of the principle of equivalence. So you don't test general relativity by this experiment unless you can measure this coefficient with enough precision. The only thing that you test is the principle of equivalence in a generic sense, and then different theories, well, indeed give you different values for the deflection angle. This is measured by gamma, but how much you can constrain the value of gamma with this experiment is not so clear. So I recommend you to read or take a look at least at these references, because some of them, they tell you the story of how this experiment was carried out and what are the problems and the results. A much better determination of gamma is obtained by the next experiment that we are going to study, which is that of the radar echo delay or the Shapiro delay, especially if instead of doing the original experiment by Shapiro, you do the experiment that was carried out using the Cassini spacecraft instead of Venus, as it was in the original situation, okay, in the original Shapiro experiment. So this is what we are going to do next. The radar echo delay, or also known as Shapiro delay, is a longitudinal effect. Remember that when we wrote for Ni, that to this order it would be given by ki plus alpha I divided by c squared plus terms of higher order. Okay, this led to velocity, which we defined as the derivative of xi with respect to the coordinate time, that was given by c1 minus gamma plus 1 u divided by c squared times ki plus alpha I divided by c plus terms of order 1 over c cubed. Okay, if one now integrates this expression to find xi, we will find that xi will certainly start with xi at the emission point. Then there is cki t minus te. This comes from the integration of this term, but there will be a term that we are not going to, we don't know yet until we compute it, that will be proportional to ki because it is constant, and that will be, we will call delta xi parallel. So this is the term parallel to ki. Okay, let me remove this index I because it will lead you to confusion. This depends on t, and we are going to define it with a c squared here. And then there will be a term which is orthogonal, okay, to k always, and which will also be a term of order c squared plus terms of higher order in c4, so in 1 over c4. So delta x parallel describes the effects which are longitudinal, and it is called, in fact, the longitudinal displacement. And okay, just by definition, if you take the derivative of this expression and compare with the expression for vi that we have there, it satisfies the equation t with respect to the t of delta x parallel, okay, which is a function of time. This is minus c gamma plus 1 u. Okay, delta x transverse is really is called the transverse displacement. It is orthogonal to ki and satisfies another equation, which is what you can expect. Okay, and it is c alpha I. Okay, so this is in the end the trajectory of the light ray is given by this expression, where these two terms here that describe the deviation, okay, from the standard of the expected trajectory of the light ray in Minkowski space-time, this one and this one, longitudinal and transverse, satisfy these two equations here. Okay, so here we are interested in computing just the longitudinal displacement, and since we know the general form of u, remember that u t and x was given by g and the integral over y of rho star t y divided by x minus y. Okay, so we just have to put this here and try to solve it. Okay, you get to this is a differential equation, and the way to solve it is to try to rewrite u as a time derivative, and in order to do this we use another trick, okay, that I haven't invented. It is, you can find it in Poisson and Will, and this trick is based on this observation that 1 over c, the derivative of the log of s plus si ki is 1 over s, okay, which is what we have here. This in this notation, this is just s, okay, plus terms of order 1 over c squared. Okay, now we are going to make use again of the fact that we are in this slow motion approximation, so the derivatives of rho star with respect to time will be also of higher order in c squared, and the whole thing is total derivative, so you get immediately that delta x parallel is minus gamma plus 1 g and the integral over y of rho star t y, and then the log of s plus si ki plus an integration constant. If you impose the boundary condition that delta x parallel at emission time is 0, you get a term which is like this one but evaluated at emission time. So when you collecting both of them under the same integral, you get that this is se plus si e ki, and this is the expression. Okay, you can still simplify it a bit more using an expression for b squared for the impact parameter, okay, which is se minus sei ki, then times se plus sei ki. If you use this expression here, then you can rewrite the integral as well, the integrand d3y rho star ty, and then the log of s plus si ki times se minus se ki, and this divided by b squared. We just use this trick to write this in terms of the same analogous expression with minus and b squared. Okay, now again we use this definition for the particular case in which rho star ty is delta 3y. So it's an approximation for an spherical object at rest at the origin of coordinates. Okay, and we are going to use also this notation that you find in Poisson and Will's book, which is well, this is the time of observation of this effect, okay, and the position evaluated at this time to call xi ops, okay, and similar expressions for the absolute value and so on. So using this, okay, you find immediately that this is minus gamma plus 1 gm, and the log of absolute value of x observation plus the product of this vector times ki, then an analogous expression but now at emission, and everything divided by the impact parameter squared. Okay, now we are using this observation time. We can come back here, and okay, this would be x of t, but let's use t as observation time. Okay, so you would have xi observation minus xi emission equal to this observation emission. Then this would be at emission, at observation time and observation time. Okay, t ops. Okay, take this expression that I just wrote here, and then compute the absolute value of both sides. So you have x observation minus x emission, okay, the absolute value squared, and then you compute that of the right hand side, taking into account that the product of the longitudinal and the transverse terms is by definition 0. Okay, so this gives you c squared t observation minus t emission squared plus this would be this squared, which is of higher order. Then there is the product of the time, this difference in time times c and delta parallel, or delta, or the longitudinal displacement. This gives you t ops minus te times delta x parallel divided by c plus terms of higher order in C4. For instance, there is a term which could be delta x transverse divided by c squared squared. Okay, we're not interested in that. And okay, we are interested in the delay, so this is difference in time. So we take c squared t observation minus te. We take the square root of this term, and in the right hand side we have the square root of x observation minus x e minus, okay, 2 t observation minus te divided by c, and this delta x parallel, okay, plus terms of order 1 over c4. We keep this comes squared, and we keep operating. So the trick that we are going to play here is that we are going to introduce a term which is of order 1 over c4, but so it doesn't really matter, but that makes completes a square here. Okay, so we introduce delta x parallel over c squared, okay, again plus terms of order 1 over c4. So this order we haven't done anything, but this whole thing is just x observation minus xe minus delta x parallel divided by c squared. Well, I realize that it doesn't look like this square immediately, but I am using the fact that ops minus xe is certainly c t ops minus te plus terms of order 1 over c. And then I can replace this, okay, by this plus terms of order 1 over c squared. This is what I have done here, and this is why the whole thing becomes this square, again an approximation to the ordinate which we are working, and you arrive to the expression t ops minus te equal to x ops minus xe minus delta x divided by c squared plus terms of order 1 over c4. Okay, now we have an expression for delta x parallel for the longitudinal displacement, and we plug it in here. But let me first divide everything by c. Okay, we are interested in this difference, not the difference multiplied by c. So this will be c5, and okay, and minus, and this expression that we derive here for delta x parallel had a minus sign, so minus and minus is plus, and then we get gamma plus 1 gm sorry, what is this? Is gm and this log of x ops minus x ops I ki, and the same for emission divided by b squared. Okay, now if light propagates at the speed of light, there would not be this term here. Okay, you would have that this difference in time would be the distance divided by c, but this is not true. Light does not propagate immediately at the speed of light, and there is a delay, and this is the Shapiro delay, although we still have to massage a bit this formula, but it will be the Shapiro delay. And I will discuss a bit later why light does not propagate at the speed of light as everybody says. Okay, so in the case of the Shapiro delay, both the source and the observer are very, very far away from the body. Okay, in the case of the original experiment, it was the sun, then the Earth, and Venus, okay, somewhere here. So you would send a radar signal, and it would come back. Okay, then the distance is really big, at least with respect to the impact parameter. And in the case of the Cassini spacecraft, instead of Venus, Cassini was close to Saturn, I think, but whether it is Saturn or Jupiter, in any case it is much farther away than Venus, so the approximation is good. Okay, and then in that case, okay, as we saw before, you can make the approximation that the product of xei ki divided by xe is more or less -1, and for the observation divided by, this is an absolute value always, okay, this is more or less +1. So you have okay, you take these scalar products and you find that T ops minus Te is 1 over C, the distance between points of emission and observation, plus gamma plus 1 gm. I forgot this factor of C cubed that is here, and then the log of 4 times x observation and x emission divided by b squared plus terms of order 1 over c5. And now this is the Shapiro delay formula. Okay, in this the experiment that I just described, the signal has to go and return. So in the return trip, the effect is doubled. So what you really measure is the time between your emission and your observation again, but you emit this emission, okay, would be the rebounding or the reflection of the light in Venus. So here you get that delta T is 2 times this result, and the difference, okay, this delay with respect to the expected value is 2 times gamma plus 1 gm divided by cq, and then this log for x of xe divided by b squared plus terms of order 1 over c5. Okay, so this is a much better formula or much better situation for measuring or constraining the value of gamma, because well, it is the setup is much cleaner. You don't have to go so close to the sun. Okay, there is no such an approximation made here. It doesn't have to be that small, and you know x ops xe with good precision. So this can constrain gamma much better than the deflection of light by the sun. A even much better determination of gamma can be achieved if well, if you do this Cassini experiment, because then you can follow this spacecraft and continue and check how this delta T, the delay, changes with time as the Cassini spacecraft moves. So in this experiment, what you really observed was this derivative with respect to time. Okay, so this is delta T, if you want, divided by 2 in this experiment. And if you take the derivative and you take into account that the impact parameter changes with time, because you are following the Cassini spacecraft, which follows Saturn, and well, Saturn goes close to the sun, and also the Earth moves, so the parameter B changes. Okay. I have put a couple of figures from the original paper, whose reference is also given in the program as recommended reading, and you can see basically how the impact parameter was changing with time in days. The second figure that I have copied from that paper represents the experimental data for this derivative, which is measured actually as frequency shift. And okay, we just have to take this formula, take up here, take the derivative, and see if what one measures coincides with the predictions, and well, in relation to how B changes with time. Okay, when we take the derivative of delta t, there are certain things that we can consider almost constant, like the distance from the point of emission, so basically the Cassini spacecraft, and the distance from the Sun to the Earth. Those two values are almost constant. They vary very slowly with time. So when we take the derivative, we can ignore them. And the result is just that, well, the derivative only acts on B. So you get minus 4 gamma plus 1 gm divided by c cube 1 over b dB dt. Okay, now you can estimate, well, you know the values of g, the mass of the sun, the speed of light. You can estimate also the value of dB with respect to dt, because B changes basically because the Earth moves. That's the fastest motion that changes B. So you know the order of magnitude of this dB, and then you can give a number for this formula. Okay. Then the point is, what you have to do in the end is to compare what this formula predicts with the experiment, and the result is that gamma is 1 plus 2.1 plus or minus 2.3 times 10 to the minus 5, which is the same as saying that gamma is 1 with a precision of 1 part in 10 to the 5. And remember that GR predicts that gamma has the value equal to 1, so this confirms general relativity with very high precision. On the other hand, other theories that predict different values of gamma, unless those values of gamma are included in this small interval, then they will be automatically excluded. And this is, well, this is the result of the Cassini experiment. This very precise measurement of the post-Newtonian parameter gamma.